All right, we have lecture 39, notes, t-score, and unusual values. You should have those out. Our context is that we have a population of data with mean, mu, standard deviation, sigma, may or may not be normally distributed. If we let X represent reaching in and drawing one value at random from the population of data, then we can think about taking samples, random samples of size n, and computing X bar for each of those samples. That's a new random variable. It's going to have distribution normal with mean mu and standard deviation sigma over the square root of n. And that's if the sample size is large enough, usually bigger than or equal to 30, or if the original population is itself normal, we have that. And the thing to remember then is that to compute probabilities associated with X bar, we convert to z-scores. And so let me just put here the z-score of X bar is, well, I take X bar and I subtract its mean, which is the same as the mean for the original population of data, and I divide by the standard deviation for X bar, which is the original standard deviation divided by the square root of the sample size. Okay. So what we're going to do is we're going to think now in terms of unusual values, and we're going to have to go back and forth between z-scores and probabilities a little bit here. So if you look what I say now, letting alpha be the cutoff probability for unusualness, and z alpha, the z-score with tail probability to its right, equal to alpha, and minus z alpha, the z-score with tail probability to its left, equal to alpha, we have, okay, in the first case here, I have the right tail case. So what I'm doing is I'm thinking of X bar values that might be unusually large. So I have X bar is normal with mean mu, standard deviation sigma over the square root of n. And the picture that we want to draw is the bell curve like this. Here's mu, and here's my standard deviation, right? Sigma over the square root of n. I guess I'll write that in one time, maybe here. Okay, and what I want to think about then is, this is the right tail case. I have over here a data value, and this area out here is equal to alpha. That's my cutoff area for being unusually large. And what we're really saying is that we have unusually large X bar values here. Here meaning, out on the number line out this way, right? Where the tail probabilities associated with those values will be less than alpha. Okay, I have my arrow here where I say convert to z-score, right? I actually give you the formula, which is this right here. So if you do that, you end up with the z random variable, normal 0, 1, right? This is normal 0, 1. And what I have out here, again, is my area alpha. And right here, then, is my critical z-score that to the right of it is area alpha. And what I'm saying is I have unusually large z-scores. Z-SC, not CS. Z-scores for our X bar. They'd be out here, right? Okay, so if I have an unusually large value of X bar, that will correspond to having an unusually large Z-score. If I have an unusually small tail probability for X bar, that means it's sitting out here. It means when I convert to z-scores, it's going to have a small tail probability out here because it's beyond the z-score, right? That's the right tail case. So I'm thinking of X bar being unusually high or unusually large. Well, the other one is the left tail case, which let me squeeze it in here. And so I have the same sort of a thing. Let me just kind of go down the line here. And so my picture now, though, is, go below there, my picture now is, here's mu, but now I'm thinking maybe my value of X bar, so this again, this is X bar here, right? It might lie back this way. So this area now has to be alpha. Okay, so I'm going to say I have unusually low or small X bar values. And those would be, you know, out here on the number line somewhere, because their tail probability will be less than alpha. And that corresponds to the z-score over here. So this, what I wrote here, is down here as well, right? Convert the z-score. And I'm looking at over here with a tail probability of alpha. And here I will have the z-score that has area alpha to its left, and that, of course, will be negative z sub alpha. And so I have unusually low z-score values. Unusually low z-scores for X bar. Again, and those would be out here, right? I'm running out of room, but out here in the number line to the left of my negative z alpha. Okay, so if I get a value of X bar and it lies way out here, correspondingly its z-score lies to the left of negative z alpha, I would say it's unusually small or unusually low. Okay, that's what we have for z-scores. And I was hoping to get everything I was going to say right here so I wouldn't have to move over here because I want to put something up here. But I guess I'll have to move over here and then, actually, no, I guess I'll rub this out and talk just a little bit. So read the next page there where it talks about what can happen if we don't have sigma. It says if we don't have sigma, suppose it might happen that we know the mean of the original population, but we don't know the standard deviation. Can we still compute tail probabilities? Well, I just said that we use the z-scores, right, to get the tail probabilities. We've done that a lot, but the z-score has sigma in its denominator, doesn't it? Because you take sigma over the square root of n. So it seems like we're in a little bit of having a little bit of a problem there, but we actually can still do it. We just have to do things a little bit differently. And if you read, I say there that we have to use, instead of z-scores, we have to use what are called t-scores. So here's what you do. I have the t-score, see, X bar's t-score, and I say versus over here, X bar's z-score. Do I have room to get the z-score in? I think I do. We know what that is. It's X bar minus mu over sigma over the square root of n. That's the key to figuring out probabilities, if we know mu and sigma. But suppose we don't know mu and sigma. What do I do here? Or suppose I don't know sigma. I mean, we know mu, but we don't know sigma. Well, the t-score is X bar minus mu divided by, I got to do a substitute for sigma. The only thing I can do is S over the square root of n, where S is the sample standard deviation. S is equal to, if you remember what I do, I take the first data point and I subtract X bar and then I square it, plus the second data point and I subtract X bar and square it, plus all the way up to, I take the last data point, subtract X bar and square it, divide the whole thing by, do you remember, n minus 1, and then square root it. All right? You did this many lectures ago. We did some computations like this. So where, you know, what I'm saying is that x1, x2, xn is the sample. That's the actual data points in the sample. So I add them all up and divide by n to get X bar, and then I do this computation and I get S. The thing is that, so I can plug that in, and that sample standard deviation sort of estimates sigma. I mean, it does estimate sigma, but it's not going to hit it right on every time, right? It itself is a random variable. When I pick a different sample, these numbers will be different, and I'll get a slightly different value for S. Right? So I'm not getting exactly the same thing that I would get if I put sigma in there. And what I say in that paragraph is, just as it is a consequence of the central limit theorem that X bar's z-score is distributed as a z-random variable, it is also a consequence of the CLT that X bar's t-score right here where S is computed using this formula, is distributed as a t random variable. And I just quickly say here the same basic requirement holds as long as the sample size is greater than or equal to 30, or as long as the original population is normal, the t-score will be essentially a t random variable. All right? And all that means is we have to use t-tables instead of z-tables. That's the big difference here, okay? So I guess I want to say here that there's only one z-random variable, if you read, this is important, but there are many different t-random variables, each with its own probability curve, and they're all kind of similar to the z probability curve. And so the values in the tables are somewhat similar, but they're not quite the same. They're not identical to the z-random variable, of course. And in fact, like I said, there are many different t-random variables. Each t-random variable has associated with it a parameter or a number that's called its number of degrees of freedom, or df, I say there. And it's always going to be a positive integer. So df is always a positive integer. Okay, and so let me draw a little picture here. I think I have enough room to do all this. So suppose I have here just this is z, right, which is normal 0, 1. What we find is that t tends to have little fatter tails, so it's above the z-axis, above the z curve out here, and then kind of comes up and maybe cuts a little lower here and comes through like that and goes off like that. All right, this is the t random variable, and I've drawn it. It's a little bit fatter, so you can see the probability is spread out a little bit more, right? And the more spread out it is relative to z, that's a sign you have a t random variable with lower degrees of freedom. So let's just say this might have a degrees of freedom being 5 or 10. Okay, if I take another one, and let me just kind of dash it because otherwise I think I'm going to just get too cluttered here. Let me take one that's just almost the normal random variable, almost z. Okay, this would be t with degrees of freedom equal to a bigger number, like 500 or 1,000. So this, or here, like 5 or 10, right? And so this could be 500 or maybe 1,000. What you find is that, excuse me, the t-curve looks more and more like the z-curve if the number of degrees of freedom gets bigger and bigger, all right? And as it shoots off to infinity, it conforms itself perfectly to the z-curve. But it never gets there because you have to go all the way to infinity to get there. So you might look at this and say, well, okay, it looks like a bell-shaped curve, and it is. Pretty much, so this is for t, pretty much a bell shape still. Okay, but it's not exactly normal. Okay, you might look at this and say, well, okay, it's spread out a little bit more. Look at the pink one here. It's spread out a little more than z. So maybe it has the same mean as z, which is 0. It sits right, it is symmetric. Symmetric along the y-axis, so symmetric over y-axis, and the mean is always 0 for all t random variables, all right? So you might say, okay, wasn't this just a normal random variable with the same mean as z, but maybe a little bigger standard deviation because it's spread apart a little more. The area under all these curves has to always be 1. The total probability is always 1. It's just spread out a little more, so maybe it's like normal 0 with a slightly bigger than 1 standard deviation. The answer is no, it's not quite like that because the shape is just a little bit different, all right? So we can't use a z with a different standard deviation. We would be off a little. We have to go to this new t random variable. And I guess, I got one more big thing to say here, but let me just go ahead and tell you that we are going to need to, well, I guess I'll go ahead and put this thing down. The next thing I want to say then, this is important. I'm telling you, you got these different t-random variables with different curves, therefore different charts, right? When you look at probabilities, which one do you use? And what I say here is, if sample size equals n, then x bar minus mu over s over the square root of n is the t-random variable, I think I can squeeze it in, is t, and the degrees of freedom will be n minus 1. Yes, I just barely got it in. All right, I think you can read that. The degrees of freedom will be the sample size minus 1. So what that means is I will have to find the chart that is for the probabilities for the t-random variable with degrees of freedom n minus 1, whatever my sample size is, n. And that's how I can compute tail probabilities. That should tell you, in fact, that just in contrast with the z-random variable, where we have all kinds of probabilities tabulated for the t-random variable, because I have a different t-random variable, a different chart, therefore, for every degree of freedom, starting at, well, you could start all the way down to 1 and go up to 10 billion and beyond. I can't have 10 billion plus charts. I'd have, book after book full of charts, and that's not reasonable. So what we do is, instead of having full charts for all the probabilities, we just have a chart that has the tail probabilities for a few values of the tail. And we only do that for certain numbers of degrees of freedom. So in particular, I guess I'm ready to do this. Let's suppose, you should find your chart, your t-value chart, and I'm going to let me go ahead and put the chart up right now. I took this chart off the web, and so what I have here is, here's the t-random variable. Notice it's pretty bell-shaped, but again, it isn't normal. And what I'm finding here is the chart will tell me the t critical value, the t-score, if you will, when I have this probability to the right of it. And what I do is I go down my chart here, and here are my degrees of freedom, all the way down. It goes up to 1 through 30, and then it starts jumping to 40, 50, 60, and then at 100, and then it goes to 1,000, all right? And what I have up here across the top are the tail probabilities. So that black area right here in this column is 0.25, is 25%. Here it's 0.2, here it's 0.15, 0.10, et cetera, all the way down to 0.0005. Okay, your chart is going to be similar to this, maybe not identical, and some of you might have a chart that has the tail probability for area in one tail and also for area in two tails, and it's the area in two tails is just going to be double the area in one tail, and we'll look at an example in a minute. But let me just do one quick example. Let's see, I think I can squeeze it in maybe right here. Yeah, all right, let me just do one quick example up here where I say the degrees of freedom is 6. Okay, what I've done is I've just told you which t-random variable I'm working with. It's, some curve here, but it corresponds to not the first, not the second, not the third, but there it is. The degree of freedom is 6. And what do I say? I want the tail probability is 0.025. So alpha is 0.025. So what's my t-score? Let me write it as t 0.025 equals, and if you look, so 0.025 is right there. So I go across here, down to there, and it's 2.447. So it's 2.447. And this is I'm going to think of it as my critical value. It's going to be my cutoff t-score for deciding whether X bar is unusually large or not. I'll look at its t-score and see, is it beyond this 2.447, for example. Okay, now what I'm going to do is I'm going to trust that you can use the table, your own table on your own, and I am going to just get rid of that, and then I'm going to try to work a few problems just in this space. Okay, so let me see here. I say, there's the quick one. Now I want to do some that I just say it's a little bit more in context. So what I'm interested in doing is looking at my value of X bar and trying to decide whether or not it's unusual. Okay, so I have the following. Sample size is n equal 41, and so n equal 41, X bar is normal with mean mu, and standard deviation sigma over the square root of 41. I'm not even giving values to mu and sigma right now. I don't need to do that for the purposes of what I'm doing here. And I just say my cutoff probability is 0.05, right? That's what I have. Yes, okay. Now what I'm doing is the right tail case. So what I have here is, this is normal curve, right? This is mu, and I'm looking at the right tail case. So out here, I have some value such that beyond here, the area equals alpha. And what I'm saying is if my x bar value lies beyond whatever this value is, I'm going to call it unusual because that's my cutoff value for unusualness. All right, well now I compute in terms of t-scores, and so I get over here, there's my t-score curve. This is t with degree of freedom equal to 41 minus 1, which is 40, all right? So I could go look in my table, and I have a right tail of area of 0.05, so I want that again. So this area here, area was 0.05. So this is my t-score, t sub 0.05. And I looked that up in my table, and I trust that you can do that. Find area in one table equal to 0.05, and you get 1.684. 1.684. So again, I'm thinking of x bar being unusually high, right? So this is, I'm just going to say, unusually high is what I'm looking for in x bar. I think if it's way out here, that corresponds to its t-score being out here, right? Okay, next one would be, what do I have? I have n is 19. N is 19, so x bar is normally distributed with mean mu, standard deviation, sigma over the square root of 19. Since 19 is less than 30, I'm assuming that the original data is normally distributed, okay? So I still have this picture, but now I'm back here, and this time I want alpha to be what? 0.01, I say. So my cutoff probability is, my cutoff area is 0.01. If I get an x bar value below there, below this value, I will say that it's unusually small. What is the corresponding t-score? Now it's going to be t over here, and the degrees of freedom are 19 minus 1 is 18, all right? So I get whatever that's going to look like, and back here is the t-score I want, and here I'm going to have area equal alpha again, and my t-score is t, you should have it looked up by now, t sub 0.01, and that turns out to be, for degrees of freedom 18, you should have found that it is, you look in the table and it's 2.552. You have to understand that you're being given the right tail version. So the left tail would be the negative of that, right? So this is actually negative t.01, and that's negative 2.552. Okay, and this is looking at, so up here it's unusually high x bar values. This is looking at unusually low x bar values, right? And the final one, which I don't think I have room for here, I'm going to come up here, is asking the kind of question that we will need to ask later on, which is, not so much is my value of x bar unusually high or unusually low, simply is it an unusual value? Is it far enough away from the mean that I think it's just unusual, whether or not it's unusually high or unusually low? I'm not going to worry about high or low so much, just is it far enough away? So I got to look in both directions, right? So what do I say there? I say we can also have a two-tailed case. Not just the right tail or the left tail, we have the two-tailed case. So let's say we have, and I'll change color, we have n equal 100. And we're doing alpha equal 0.01 again, alpha equal 0.01 again. And so we have X bar is normally distributed with mean u, standard deviation sigma over the square root of 100, which would be sigma over 10, actually. Excuse me. And so our picture is, whoops, I don't want a vertical bar here because I don't know where on the x-axis this bell curve actually lies, right? But so here's mu. Here's our normal distribution for X bar. Now, what does it mean to be just simply unusual? It means I could be way the heck out here, or I could be way the heck out here, all right? If my cutoff probability is 0.01, the way I'm going to interpret that is half the probability is here, 0.005 for the area. And over here, 0.01 over 2 equals 0.005 equals the area. All right, so what I've done is I've taken that probability, because it's a two-tailed situation, and I've split it in half. And I'm keeping things symmetric about the mean, all right, so that my unusualness will occur if I go the same distance this way as that way, okay? As long as I go beyond this value out here or beyond this value back this way, I'll say, oh, it's unusual based on this cutoff probability criterion. Well, what does that give us then in terms of the t-score then? We have, do this again. So this is the t random variable, and degrees of freedom are 99. All right, and what I'm looking for is the cutoff value t-score here and here. They're supposed to be symmetric, So, and I want the area here to be 0.005 and the area here to be 0.005, right? So what I really want is my critical values, which is what we call these t-scores. Their critical values are plus or minus t sub 0.005, right? Because I had to cut it in half. Okay, so I go to my table, and as with most tables, I can't do every single degree of freedom from 1 to, a billion or whatever, so they start skipping. And you'll find that probably in your table, you don't have degrees of freedom equal to 99. All right, so what do? One can make an argument that you should always pick the number of degrees of freedom from the table that is closest to this, but smaller. And the reason for that is if you pick smaller degrees of freedom, that means the curve's a little bit flatter out. You'll get values a little bit farther out that way, and so it's a little bit harder for an X bar value to be considered unusual, a little bit harder for the t-score to get out there. And there are reasons for doing that. Sometimes they're not necessarily good reasons. Often they are, though. But we're not going to get into all that. We're just going to say the following. If you don't have the degrees of freedom, just pick the closest one in the table, whether it's a little bigger or a little smaller. So we're going to use 100. The truth is, if you use software to do this, it'll compute it for the correct or approximate it for the correct degree of freedom anyway, of 99. So for the use of the table, we're just going to use 100. So if you do that, you get, you should be able to go in there and find, you can do it two ways. You can find the area in one tail equal to 0.005, or if your table allows it, you can find the area in two tables equal to 0.01. It's the same answer. You should get plus or minus 2.626. All right, and so in this case, we would just say over here, we just have unusually high X bar values. Here we have unusually low X bar values. Here we just have unusual X bar values, right? They're far away from the mean if they're out here. Their t-score is far enough away from 0 that we call them unusual, whether they're out here or out here. All right, we'll stop there.